Hello, Chemistry 131 students. This is going to be a video prepping you for some math and concepts you'll be using in your acid-base and solubility lab activity. Well, just getting into pH. It's really a measure of how acidic or how basic an environment or a solution is. And there are three main regions. If the pH value is below 7, that means you're dealing with an acid or you're an acidic solution. If your pH equals 7, then that solution is neutral. And if you're working with a solution where the pH is above 7, that is either a base or a basic solution. Essentially, when you add an acid to a solution, that acid will lower the pH of that solution, make it more acidic. Whereas if you add a base to a solution, that will raise the pH of that solution, making it more basic. A concept called neutralization is simply taking an acid and a base and reacting them together, essentially neutralizing them. One example could be taking an acidic solution and neutralizing it by adding base to that solution. Another example could be taking a basic solution and adding more acid until all the base is neutralized. Either way, once all the acid and base are fully neutralized, that's when the pH will be neutral or finally equals 7. And a common example of a neutralization reaction is hydrochloric acid reacting with sodium hydroxide to form sodium chloride and water, where essentially an acid and a base neutralize each other to form some neutral salt and water. As far as how we represent the term concentration, essentially if you want to represent the concentration of something, all you do is you put that formula between brackets. So if we're ever working with a concentration of hydronium ion, that would be H3O plus placed between brackets. So taking the formula and putting it between brackets. If you're looking at solving something involving the concentration of hydroxide, we just represent that as brackets surrounding OH minus, surrounding the formula for hydroxide. So if you see a formula surrounded by brackets, that just means concentration of that thing. And while there are multiple different formulas used for acid-base chemistry, really the ones highlighted in blue are the only three you're going to need for lab. And that is the first one on the left, pH equals the negative log of your hydronium ion concentration. If you already know what the concentration of hydronium is, you can use that to calculate the pH of that solution. The opposite is also true. Essentially, hydronium ion concentration, if you don't know it, but you do know the pH, just simply take 10 raised to the negative pH power. If your pH is 2, then the concentration of hydronium ion is just 10 raised to the negative 2 power. And on the bottom right is just a formula for if you know hydronium ion concentration or if you know hydroxide ion concentration. You can solve for the one that you don't know because hydronium ion and hydroxide ion concentrations multiplied together always equals 10 to the negative 14th power. So if you know either hydronium or hydroxide concentration, you can solve for the missing one. And we're going to go through some examples of what you might see in your lab activity. Taking this chart right here, where we essentially are asked to fill in the missing blanks between either hydronium, hydroxide concentration, pH, and also determining if that solution under those conditions would be acidic, basic, or neutral. And just going for the first horizontal row, what we already know is the concentration of hydronium ion, H3O+, and that would be 1 times 10 to the negative 8th molars, or moles per liter. Essentially, what we can do is either solve for pH or hydroxide ion concentration relatively easily if we already know the hydronium ion concentration. And if hydronium ion concentration multiplied by hydroxide ion concentration is just 10 to the negative 14th, then we can rearrange all that to have 10 to the minus 14th over our known hydronium ion concentration. And that will just equal whatever our actual hydroxide ion concentration is. So essentially, if we want to know what hydroxide ion concentration is, that's just going to be 10 raised to the negative 14th power divided by what we already know our hydronium ion concentration to be, which is just 1 times 10 raised to the negative 8th power. And essentially, whatever that equals, that will be our hydroxide ion concentration. And that came out to be 1 times 10 raised to negative 6th molars, or moles per liter. Now, we already know our hydronium ion concentration. So, in order to solve for what the pH value is, we simply just need to take the negative log of whatever our hydronium ion concentration is. So, that's just going to be negative log function of whatever hydronium is, which in this case would be 1 times 10 raised to negative 8th molars. And whatever that comes out to be, that will be the pH of our solution. So negative log of 10 raised to negative 8th power, that would come out to be a pH of 8. So in this case, our hydroxide ion concentration is simply 1 times 10 raised to the negative 6 molars, whereas our pH came out to be a pH of 8. And if the pH is above 7, then that basically means our solution is basic. Now, going on to the next row, this row we already know what the hydroxide ion concentration is, 10 to the minus 13th molars, or moles per liter of hydroxide ion. Well, if hydronium multiplied by hydroxide concentration equals 10 to the negative 14th, then just rearranging everything to solve for hydronium ion concentration, we get 10 to the negative 14th divided by hydroxide ion concentration. Therefore, to solve for what the value or the concentration of hydronium is, we're just going to take 10 to the negative 14th divided by our hydroxide ion concentration, which is just 1 multiplied by 10 to the negative 13th molars. And this will just give us 10 to the minus 1st power. Equals 1 times 10 to the negative 1st molars. And now that we know what our hydronium ion concentration is, to solve for the pH, we just need the negative log of whatever that hydronium ion concentration is. So negative log of 1 times 10 raised to the negative first power. And, well, that's just going to come out to be 1. Therefore, the pH of this solution will be 1. pHs below 7, they are acidic. And in this case, being very, very far below 1 means this is a very acidic solution. Now the following row, the third row, we only know what the pH is, but that's all right. One of the formulas we had was simply relating or solving for hydronium ion concentration if you already know the pH, which in this case is going to be our lower formula down here. Whatever our hydronium ion concentration is, to solve for that, we just need to take 10 raised to the negative pH. Or in other words, if our pH is 3.5, then if we take 10 raised to negative 3.5, whatever that equals, that will be our hydronium ion concentration. So 10 raised to negative 3.5 comes out to be about 3.16 times 10 to the negative fourth molars. So 3.16 times 10 raised to the negative 6 moles per liter, or molars. And since now we know the hydronium ion concentration, we can plug it into our other rearranged formula to solve for hydroxide ion, or OH minus. And therefore that's just going to be 10 raised to the negative 14th power divided by our hydronium ion concentration of 3.16 times 10 raised to the negative 6, or I should say negative fourth molars. And whatever that comes out to be, that is going to be our concentration of OH minus, or essentially hydroxide ion concentration. And that comes out to be about 3.6 times 10 to the negative 11th. 10 raised to negative 11th molars of OH minus. And since our pH was already given to us as 3.7 or 3.5, that is below 7. Therefore, this is an acidic solution. And for the last row, this is very simple. We're already told that this solution is neutral. So right off the back, that tells us that the pH has to be 7. And just like the prior example where we already knew the pH, we can just solve for the hydronium ion concentration by taking 10 raised to the negative 7th power, or taking 10 raised to the pH, but the negative of that pH. And well, if we do that, we can just leave this as our answer, 10 raised to the negative 7th power, or 10 raised to the negative 7th molars, which would just be the same thing as 1 times 10 raised to the negative 7th. And since we know what our concentration of hydronium ion concentration is, the only thing we need to do is take 10 to the negative 14th divided by our hydronium ion concentration, and that will be our hydroxide ion concentration. And well, 10 raised to negative 14th power divided by 10 raised to negative 7th power. That is just going to also equal 10 raised to negative 7th molars or moles per liter of hydroxide ion. So that last row was really just, if you're told you're working in a neutral solution, you can automatically assume that you're working with a pH of 7 and then go from there. Now, one thing that we should touch upon is essentially what actually is concentration. So whenever we have brackets with something in it, we're actually talking about the molarity of that thing. And molarity of whatever you're talking about is really just moles of something divided by the volume it is dissolved in. So let's look at some example problem that you'll see in your lab worksheet. A sample of 0.005 moles of HCl was dissolved in 2,500 milliliters of water. Calculate the molarity of this HCl solution, then the concentration of H3O plus or hydronium ion, and then calculate the pH. Well, to calculate the molarity of HCl, all we need to know is what's the moles of HCl and what's the volume in liters that is dissolved in. We're already told that the moles is 0.0050. And as far as liters go, well, if we're working with 2,500 milliliters, just divide that number by 1,000, which would be 2.5 liters. And what this gives us is 0.005 divided by 2.5 liters, which would be 2 times 10 raised to negative third molarity, or moles per liter. Moles per liter, or capital M for molars, is the same exact thing. And just to write this fully out, that would be molarity of HCl. Now, molars of HCl, that's just moles per liter. If we want to solve for what is the concentration of hydronium ion concentration, but we only know the concentration of HCl, that's actually very simple. So 2 times 10 to the negative third molars of HCl is just 2 times 10 to the negative third moles per 1 liter of HCl. And this is going to be similar to our mole to mole calculations that we've done for stoichiometry. Let's look at our top reaction. HCl reacts with water to form hydronium ion and chloride ions. And in this particular situation, the reaction is already balanced. So, if hydronium ion concentration, or H3O plus surrounded by brackets, is really just moles of hydronium ion per liter, well, that's actually very simple to calculate. We already have 2 times 10 to the negative third moles of HCl per liter. Let's change that moles of HCl to moles of H3O plus. And we'll just need to multiply by a ratio of our moles of HCl, of our moles of H3O plus, divided by our mole ratio of HCl. And well, our mole ratio is just going to be, in this case, going by the stoichiometry of our reaction, 1 mole of hydronium ion is produced for every 1 mole of HCl that is reacted. And all this does is essentially it crosses out the moles of HCl so that we're left with just moles of hydronium ion concentration per liter. Now, that was just a long way of saying if you're ever given a concentration of something, that's just moles of that something per liter. And if you need to convert it to a concentration of something else, you'll just need to multiply by a mole ratio of whatever you want to end with over what you're starting with. And we've already done mole ratios through stoichiometry. Now, essentially, all we did was, because this was an easy 1-to-1 mole ratio of every 1 mole of HCl reacts to form 1 mole of H3O+. The starting concentration of HCl is also the final concentration of H3O+. In other words, that's what the concentration of H3O+ is. And since we know what our concentration of H3O+ is, we just take the negative log of that value to get our actual pH. So negative log of 2 times 10 raised to negative third power. That will give, let's see, that will give 2.70 as our pH value. So in your worksheet for lab, you're going to have one problem that tells you moles of something and the volume it's dissolved in. Just divide the moles by the volume in liters, not milliliters, and that will give you your molarity or your concentration of that starting compound. And then it's very easy to just convert from concentration or moles per liter of that thing to moles per liter of a new thing, just using stoichiometry. And then when that gives you the concentration of hydronium ion, you can plug that into our pH formula to solve for pH. And that's really all that's necessary to know before getting into acids and bases, except for one more component, which is buffers. You are going to be asked if you're working in a buffer solution for the last part of your acid and base experiment. And really, buffers, they're very straightforward. A buffered solution is really something that is resistant to sharp changes in pH. What that means is that buffers, let me rephrase this. Buffered solutions are resistant to sharp changes in pH. They don't like to change the pH doesn't rise up easily or lower easily or quickly if you add acid or base. Buffers can be acidic, neutral, or basic, but what's important is that it's very difficult to change that pH value. Either it's hard to actually raise it by adding more base, and it's also hard to lower that pH value if you add more acid. So, adding acid to a buffer solution will lower the pH very little. And if you add base to a buffer solution, it will raise the pH very little. And typically you'll need to add a lot of acid or a lot of base to see even a little bit of change away from your starting pH. You'll know if you're working with a solution that is not a buffer if when you add acid, it lowers the pH a lot, or it lowers it very easily. And if you're adding base to an unbuffered solution, it will raise the pH a lot or very easily. Essentially, if you're working with a buffer, it's hard to change the value of the pH, but if you're working with a solution that's not a buffer, it's very easy to lower or raise the pH value. Now, your second lab activity is just going to get into a modest amount of organic chemistry. And really, much of it is very easy to know. We'll cover more in-depthly in lecture. But here's essentially 2 parts to talk about. For part A of your lab activity, for the second lab activity, when I ask for the type of bond, it's really asking, are you using an ionic compound or a covalent compound? Are those ionic bonds or are they covalent bonds? So for example, something that consists of just ions that are attracted together, like say sodium chloride, that would be an ionic compound. Whereas anything else that is not simply charges attracted to each other, but actual sharing of electrons, when we were drawing Lewis structures and drawing in chemical bonds as dashes, that would be a covalent compound formed through covalent bonds. Now, a second type of classifying different compounds would be, are they organic or inorganic? And something is organic if it consists of a lot of hydrogen-carbon bonds. So if there's a lot of carbon bonded to hydrogen, there can be other elements like oxygen as well, but as long as there's a lot of hydrogen-carbon bonds specifically, then you're using an organic compound. But if your compound does not have any hydrogen-carbon bonds in it, then that would be an inorganic compound. Just like sodium chloride is just sodium ionically bonded to chlorine, there is no carbon-hydrogen bonded in that formula. So it's inorganic. Now, as far as part B for solubility, here's just an important concept to know. Water is a polar solvent, and it will always be the inorganic layer, or the polar layer. Inorganic molecules dissolve in the inorganic layer, while cyclohexane is a nonpolar molecule. Therefore, it will be what the organic layer is. Just some more background. Essentially, if you have water and cyclohexane mixed together, you're going to see 2 different phases or 2 distinct layers. Whichever one is more dense, water or cyclohexane, that will be the bottom layer, and the less dense fluid will be the top layer. Water will be the polar layer or the inorganic layer where inorganic molecules will dissolve, and cyclohexane will be the nonpolar organic layer where organic molecules will dissolve in. And for this part of the experiment, essentially, if whatever you're working with dissolves in water, then that is going to be an inorganic compound. But if what you're working with does not like to dissolve in water and instead likes to dissolve in cyclohexane, then that will be an organic molecule. And that just covers really everything for this prep video for the acid and bases and organic chemistry solubility lab activities. Well, peace out.